record. Right, recording started. It's Friday, January 14. Going to do a Ripple Tank demo, finish the homework questions and do some Doppler questions. So here's Ripple Tank, got some water in it. Turn this square. Okay, there we go. Oh, and you guys see this plastic peg right here. This is going to vibrate up and down. So with some frequency, some number of hertz. It's going okay. Now what I do is take this plastic arm. You guys see the shape of this plastic arm? Right. This is going to plug in right here, and this is going to reach over and touch the top of this water right here. That's how it's working. So see what this looks like. Ooh, oh, look at that. Set up a standing wave. I set a nice standing wave and have a knob. I can change the frequency. Can you guys hear that? Hear the hum? See, it's like a low frequency, and then it goes. Now, as I'm adjusting this knob, changing the frequency, what's happening to the speed of the waves in the water? The speed? Is that changing? No, yeah, the speed's the same. Yeah, you guys are right. The speed of these ripples through that medium, in this case water, is just whatever it is. Okay. Now, if the frequency is changing, oh, hold on. If the frequency is changing, but the speed is the same, that means what other physical property must be changing? The wavelength. I'm thinking wavelength. Okay. Now, if you're thinking amplitude, that's like out of the page, like third dimension, like towards the camera, would be amplitude. You have to get like down on the water level. But yeah, like the distance between like crest to crest, right there. Yeah, that could be like wavelength. See how the lower frequency has a long wavelength and a higher frequency has a short wavelength. You got that. Now I can pop some different stuff in here. So I'm gonna do that. Maybe like this shape. Like what if I pop in this flat wall? What's that gonna do? Ooh, we get some reflection going on. I see some reflection and hey, kind of like an interesting interference pattern. Okay. You turn this around. One property of waves is that they, when waves interact, they can create an interference pattern. You guys know about constructive and destructive interference. So that happens periodically. You've got some kind of interference pattern. And the reason I'm bringing that up is because that's one way you can mark the definition of a wave, which is going to be important. Here, I'll try this one too. When we get near the end of this semester, I'll tell you guys about quantum mechanics, which involves physics of really small things like atoms. And when you get down that size, that scale, interestingly, there's this wave-particle duality. So what is, say, an electron? Is it like a particle, or is it like something that has like wave-type properties? Well, if I were to say different electrons and they create some kind of interference pattern, that might actually be evidence that it fits into this type category phenomenon, or it's like some kind of wave going on. Okay, some kind of, well, that one worked. Okay, once. What if I do this? I'm gonna take off this piece and replace it with this guy. Ooh, look at that. There's two. Oh, what this is gonna look like. Maybe this is a better example of those interference pattern I was saying about. That. Try popping different stuff in here. Try this guy. And got one more nozzle there. One more of these. Replace that guy with this guy right here. Ooh, look at that. That's a straight edge. What do you think this is going to look like? I toss this and make like a straight edge wave. This is going to look like. Oh, hey, like straight waves. Look at that. Turn frequency down too much, it's kind of wonky. So we've got some reflection off the side, some interference going on. How about pop some stuff in here? do one more of these. Try this guy. All right, so pretty cool. All right, so put the ripple tank away for until next class for me. All right, what else we got lined up here? All right, so yesterday we actually did most of the homework. Just got, I think, one problem left to do. So we'll knock that one out. Let me get the lights on. You guys ready for lights? Lights. Okay. Knock out this problem and then we'll switch over to do some Doppler stuff. Okay, so this page, chapter 15, the last one we left off on, you guys remember number 71 involves a vertical tube in the water. Next week, I'll have lined up for you guys a lab that's basically very similar to that problem. It measures something a little bit different. But the last one we need here is at number 93, guitar strings. Equation for the speed of a wave on a string. Ooh, this is new. I haven't told you guys about this yet. The speed of a wave on a string, V equals the square root, tension force divided by linear mass density. They go define those parts for you guys here. So suppose a guitar string has this mass, like so many grams, it's so many centimeters long. What should the tension in the string be to produce a note whose fundamental frequency is so many hertz, right? Which would correspond to a musical note? Yeah, jot this down. Start solving this thing and then get my camera too. So number 93, not here. Okay. So we're gonna have a guitar string vibrating. I said fundamental frequency. Now think about how that works for strings, like a fundamental frequency. Okay. Is it gonna vibrate up and down like this? Let me just, I'm gonna switch my camera over real fast and share a video demo for you guys. Show this in real time. Okay, so got modes on the string. You got the oscillator on the left. There's a string that's pulled taut. That oscillator is gonna bounce up and down. Yeah, you guys see it oscillating up and down. Okay. And there are certain places where it'll set up standing waves. I don't see a standing wave there, but oh, right there. Okay. So call that 11 hertz. You guys see it. Guys, how many wavelengths is that? Well, half a wavelength, right? Because I see a trough here, and then the crest would be the other half, or I mean, it's kind of blurry there. So, crest and we need a trough. So that's half a wavelength. Then speed this thing up. Right, so there's no standing wave until you get to 22 hertz. Now there's a standing wave. That's one full wavelength. You see one full S shape, one full wavelength. Right, keep bumping up the frequency. If you do 25 hertz, 28 hertz, you get looks all muddy, but 33 hertz looks like that. Right, so you guys see the pattern. That's 1/2 wavelengths. That's two wave. There's 1.5 wavelengths. There's 2 wavelengths. Right, keep on going up. But we're interested in this right here. This is the problem we're solving. So fundamental frequency for say a vibrating string like that would be half of a wavelength. Okay. So switch my screen back over. Okay. We're going to call from here to here. This is the length of the string, but it's also half of the complete wavelength. Okay. That'll be important in a few minutes. Okay. They told us some things here. They told us the mass of the guitar string, the mass of the string. Okay. I'm going to jot down the numbers. I'll go ahead and use the book numbers for this one. I know you usually change them. They said how many grams? They said 3.2 grams. I'm going to change that to kilograms. 0.0032 kilograms, because we do everything in kilograms, right? Okay. 3 decimal places, go from grams to kilograms. They told us the length of the string, L. They said 65 centimeters. Isn't that 0.65 meters? Okay. And the target frequency, say F, right, which would correspond to some musical note, say 147 hertz. Right? It's going to play some note. Right? And the question is, what is the tension in the string to make that happen? Demo for this guy, guys real fast. If you're looking at the head of the guitar, let's say I'm going to plug this this fat string right here, this E string, right? And then you can adjust it with this knob, which you're popping apart here. Put together. All right. Right. Well, okay. I'll show you guys. This tuner. Battery here. Needs to like rest on the guitar so it can vibrate and pick it up. I don't know why my production doesn't pick that up, but it does, or I don't know if you guys can see it, says E, like an E note, but I can change this, give it more slack, drop down to D sharp, and then increase the frequency, increase the tension. That's like an F sharp right there, right? Then I'm gonna pull that back down to E. Okay. So what I'm trying to demo for you guys is that the tension that you pull the string is related to its frequency. If you give it more tension, it's going to up the frequency. So that aside, okay, so we got these properties of this particular guitar string, but we need an equation. We're actually going to need two equations. They gave us one of them. They listed this. It said speed of a wave on the string is equal to the square root of tension force due to tension, divided by linear mass density. Okay? I'll talk about this a bit. All fall semester, I tended to write tension as just capital T, but you got to be careful with that in this particular chapter because capital T could be time period. So F sub T. Okay, well, it's force due to tension, like a tension force. And this Greek letter mu you've seen in the past, it could be the prefix micro. We were also using it as a variable as coefficient of friction in the past, but in this context, it means linear mass density, like how many grams per meter, sort of thing, or kilograms per meter. Right? So, okay, so if you had like a little skinny string, it might be a very small linear mass density, or the big fat string, that's a lot of mass per unit length. That's what this is, mass per unit length. Right, and this question again, the question is, what should the tension in the string be? So here's our end goal. Our end goal is to solve for this tension force. Right? Okay, so seems all right, right? How are we gonna do this? Well, I know linear mass density, that's probably mass divided by length. So these two numbers are going to feed into this variable, right? This divided by this. So I see how that's going to pop in. Okay. How about the speed of a wave on a string? Okay. Well, don't have anything like speed, but I know a different formula. So a little division here. Okay. You guys remember wave speed is equal to wavelength times frequency, right? Our wave formula. Okay, I see where this going because we know the target frequency. That's that number. Feed in right there. And the wavelength. I know half the wavelength is the length of the string, so 2 times the length would be the wavelength. Yeah, and I know the length of the string. Okay, so now we have enough parts. You guys see how all the puzzle pieces are going to be able to fit together now. Okay? So kind of a complex problem, but that's okay. Yeah, let's do this. If speed is equal to this expression and speed is also equal to this expression, then I just like feed those together and say that the square root of tension force over linear mass density is equal to wavelength times frequency, right? Speed is equal to that, speed is equal to that. Oh, well, they must be equal to each other. Like that. Okay. And then let me substitute out this lambda wavelength with, see if I cross multiply the 2, I'll get, so basically you need twice the length of string to get a full wavelength, right? So this right here is 2L. So we got square root of tension force divided by linear mass density. Actually, while I'm doing substitutions, I'll go ahead and replace linear mass density with mass per length, right? Just as a fraction right there, fraction within a fraction inside a square root. Okay. Is equal to, okay, instead of lambda, I'm going to have 2L because twice the length of string would be the wavelength. Okay. I know I've been solving a bit in terms of variables. Yeah, let's go ahead and solve some stuff. I guess I'll go ahead and plug in numbers at this point. Right, so you need to plug in numbers at some point, right? So I got square root, taking it from here, big old square root of the tension force that we're solving for. We're trying to figure out how much tension we have to give the string to hit this target frequency. Okay. divided by linear mass density, mass per length. So remember, it was a tiny number of kilograms per this length. So do that in right here, 0.0032 kilograms divided by 0.65 meters. Right? Then we've got a fraction within a fraction. So we go. And then that's equal to 2 times the length of the string, which is 0.65 meters, times the target frequency, which is 147 hertz. You guys remember hertz is like 1/seconds, so speed meters times 1/seconds, like meters per second, which describes a speed, doesn't it? All right. So we've taken care of all the complex physics bits. The rest of this is just going to be algebra. We'll just do algebra to take us to the end. So I'm going to square both sides. So while I'm at it, since I got a fraction within a fraction, I'll dump this upside down. So you don't necessarily have to do these particular algebra steps, as long as you do something that gets to the correct answer. There's different ways to do it. But take the bottom fraction, flip, multiply is one way to think about this. It's equal to, let's see, what is 2 times 0.65 times 147. But then don't forget to also square both sides. Remember, I squared the left side to get rid of the square root, so I have to square the right side to balance that. So square that, that's going to be this number. I'm getting 36519. That would be the square root unit, meter squared per second squared. See, one of the meters is going to cancel. The kilograms is going to multiply up. That'd be give me kilogram meter per second squared. Kilogram meter per second squared. That's also called a Newton. Which describes a force, like a tension force. That's the next step, though. I'm just thinking ahead. So take this number, multiply by 0.0032 kilograms, divide by 0.65 meters, and the tension you need on that guitar string is 179.8 newtons of tension, about 180 newtons of tension. For comparison, your largest lab weight, 1 kilogram, weighs about 10 newtons. So I guess it'd be like having 18 of these. If you had a string hanging, and 18 of these hanging from it, that's what you need for this particular guitar string to hit that frequency. You guys got that? So there you go. I've knocked out all the official homework problems. Anyway, if you want to turn in the homework early, you always can. If you wanted to get off your hand, I do need to write you guys' quiz over the weekend, so I do that. But take care of all those. Do you guys see flipped to the right side of your desk a page that looks like this? Actually, you have a half page and then okay. You guys see a page that looks like this? There's like a car in motion. Right, so there's a bunch of Doppler equation questions here. One of the reasons I made a whole page of these questions is because I like this Doppler formula because the fact that it has some plus or minus signs, a really good way to navigate it is, well, you have to apply some critical thinking to like what kind of motion would result in, say, an increased or decreased frequency, and therefore would you have to add or subtract on the top or on the bottom to get to that result. Okay. So now my numbers are going to be different than your numbers, but we all have the same story. So there's 4 scenarios on this. Scenario 1, 2, 3, 4, different stories going on. In the first one, well, there's a car in motion. So car in motion and a couple of people. One that the car is headed towards and one person the car is headed away from. Like person A, person B. The car is going left to right. I told you the speed of the car right here, how fast it's moving left to right. I also took, this car's honking its horn with some frequency. Now my frequency says 440 hertz. You guys have a paper that has a different number on it, but that sort of corresponds to like a musical note, doesn't it? I think 440 hertz is defined as like an A note. What frequency of the car horn does someone hear inside the car? Well, if you're traveling inside the car, say along with the car, then don't you just hear what you would hear like as if you were at rest because there's no relative motion? Or if you really wanted to be strict according to this formula, it would go like this. So there's some source frequency. This is like if the car is parked, in my case, 440 hertz. And then, well, remember if it's parked, then the observed is the same thing as the source, so there's no motion. But what if the car's in motion? Well, if the car's in motion, then you got speed of sound, speed of sound. That would be here would be the speed of the car because the car is like the source of the sound, right? But the observer would also be along for the ride. So you might be doing like speed of sound minus 25 meters per second here, but then you'd be doing speed of sound minus 25 meters per second up here. Okay. And the net effect is that this whole ratio would just be equal to 1. So, okay, so as long as you're traveling with the car, you would hear the same thing as if you were parked. So whatever the actual frequency is, just go ahead and copy paste that number right here. Okay, so that box is equal to this box. Okay. Guys get that? So don't write 440, just write whatever the car horn frequency is on your paper. Okay, next couple questions. What do each of these people hear? So person A, now person A, the car is going away from. Does person A hear a frequency that's less than or more than 440 hertz? What do you guys say? Less than, right? It's going to be a lower tone. So if this is like beep, beep, this guy hears like beep, beep. Okay. And later on, this guy's going to hear boop, boop. I'm exaggerating a bit. You guys did it. Okay, so let's run the numbers. Run this equation. So we got the observed frequency for person A is equal to the source frequency. Okay, multiplied by, okay, they get a big old ratio. Remember, it goes speed of sound, shows up there and there. Okay. You can have a plus or minus speed of the observer, and then plus or minus the speed of the source, like the car in this case. Okay. So frequency observed by person A is going to be, my source frequency was 440 hertz, different for you guys, multiplied by the ratio. On this paper, let's use 343 meters per second for the speed of sound. 343 meters per second. Now, well, if the observer is just standing there, you can say plus 0 on top, so that doesn't really require a whole lot of thought. The top's just the speed of sound. The numerator is just the speed of sound. Denominator. Okay, now here's where the critical thinking has to kick in. Okay? I know the speed of the car is 25 meters per second. A fast car. Go on. All right, and you guys told me that the observed frequency needs to be a number that's smaller than 440. I don't know, maybe like 400 or something, or like 390. I don't know. We're gonna find out. So to get to that point, would you have to add or subtract on bottom? You would have to add, yeah, right? Because that blows up the denominator bigger. Doesn't that make this whole fraction less than 1? Okay, and then 440 times something less than 1. Okay, that will give you a smaller frequency. Right, that's how we're going to do this. 440 times 343 divided by 343 plus 25. Looking at 410 hertz. Yeah, that looks believable. I could do that. 410. This box right here. Okay. Okay, how about person B, who the car is headed towards? Okay. Frequency observed for person B. Okay. Well, take the source frequency, 440 hertz, times. You guys see it's just going to be one small change. Okay? The numerator is still 343 meters per second because the guy's just standing there. But the denominator will be 343 meters per second for the speed of sound. And then you guys see it's going to be minus 25 meters per second. Okay. Anytime a frequency is moving towards an observer, you're going to subtract on bottom. Okay? Because that makes the denominator smaller, which blows up this fraction right here in parentheses larger than 1. Okay, so we're going to take the source frequency of 440 and be effectively multiplied by something greater than 1. I wanted to show you guys this too. On this calculator, if you just scroll up and scroll over, you can just very quickly pop in a minus sign where there used to be a plus and get the answer that way. One reason I really like this model calculator, it saves you some work if you have like many iterations of the same equation. I'm looking at 475 hertz. Yeah, that looks about right. That looks believable. So go with that. 475. This box right here. You guys good? Yep. Okay, so let me see what goes on. Yeah, I know what it is. Okay, it's right here. Need a second insert. Let's see. Is everybody getting numbers that look reasonable? You think reasonable numbers?
Yes.
Okay. Because if you get something like super crazy, then it might be a matter of like possibly grouping numbers and parentheses. I should have written this way. See this denominator? For example, in the calculator, you have to group this together. You have to communicate that to the calculator. Otherwise, you get something crazy. Next question. Car travels at say same speed as before. The car horn is the same frequency as before. So let's say that this person B is now running towards the car. Right? So it's almost like the question we just answered, but with one change. The person is now running towards the car. Is if this person is running towards the car, what's that going to do to the perceived frequency? Is it going to bump it up a little bit? Yeah, so this box, I bet on my paper has to be a little bit more than 475, right? A little bit more. Okay. And I can do that by starting from here. And so frequency observed for person B now is going to be 440 hertz multiplied by big old ratio. Let's see, 343 meters per second. I know the car is headed towards the sky, so it'll be minus on the bottom, minus the speed of the car. Okay. But running towards the car at 5 meters per second, should you add or subtract on top? Add. Okay. So if two objects are headed towards each other, like the source and the observer, then you subtract on bottom, but you add on top, because each of those would increase the observed frequency. Okay. So it's 440 times 343 plus 5 over 343 minus 25. I'm looking at 482 hertz. Is that right? $482. Okay, all right. Okay. So guys, what? We got about 2 minutes to the bell, so here's where we're going to finish this off. I'm not going to pick up this page. This is just extra exercises, but I want to tell you how to do the last couple right here, just in the last couple of minutes. So this next one involves a car rolling down a hill, and the sky right at the bottom of the hill is running away from the car. I think you guys can figure this out, but there is a middle step that goes back to fall semester. First you have to figure out what is the speed of the car by the time it gets to the bottom of the hill. Okay. Based on the hill height. I told you what this hill height is. Could you guys figure out what the speed of the car is, having rolled down some hill height? Could you guys figure that out? The speed of the car at the bottom is going to be this. The square root of, I bet some of you guys remember, the square root of what? What? 2GH. Yeah, you guys remember that. Kinematic motion, conservation of energy, they both gave us this. The speed of the car at the bottom is square root 2GH. After you do that stuff, then you can go back to Doppler equation and plug in that number right here. This is square root 2GH right here. And the last scenario, because that scenario is 1, 2, 3, and 4. So scenario 4. Okay. Ooh, looks like this car is on rocket boosters. You guys see some rocket boosters? Okay. The speed of this car, 600 meters per second. Guys, 600 meters per second. Hey, that means this car is going so fast, it's going faster than what? Faster than the speed of sound, faster than sound. This is greater than 343, isn't it? This car is supersonic. I bet there's some kind of sonic boom going on behind this car. Look at person G right here. What reaches this person first? The car or the sound waves from the car? The car. Does this person even hear the car coming? No. How about this last question? What does the person hear? This is a trick question. What's the answer? Yeah, here's nothing. No sound. Okay. So just bam, perfect from all. You guys got any questions? Yeah. Like I said, I'm not picking up this page, so it's just extra exercises if you want those critical things. Okay. You guys have a great Martin Luther King Jr. 3-day weekend, and I will see you guys on Tuesday.